Yes.
How many homeworks do we have left?
What?
How many homeworks do we have left?
At most one. I mean, there's one that's due what? Wednesday. And
Oh, is there?
yeah. And I may assign another one, but I haven't yet.
Wednesday's the last day of class.
What?
Wednesday's the last day of class.
You'll never
Yes.
see it.
Yeah.
Really?
Yeah, it is.
All right. I'm not a big fan of exams. So instead of a final exam, there's going to be another lecture.
When?
Whenever, presumably, the first Monday of exam week.
At the same time?
Yeah.
What if we're gone?
What if what?
What if we're gone?
Well, you'll miss it.
That's why it's for you.
Alright.
But,
There's a lot of questions there.
sorry,
What if?
so I think that's reasonable, right? I mean, I know when I was a student, I'd much prefer a lecture to an exam. I was influenced, by the way, years ago by a book I read, a couple of books I read by B.F. Skinner, who was a Harvard psychologist, professor of psychology at Harvard. And he basically showed that for various animal species, positive reinforcement was the effective way of teaching animals something, and that punishment and fear did very little, were essentially useless. And so I sort of adopted that approach to life more generally. Whether that's, well, my colleagues, of course, completely disagree. What are we going to do? All right, any other questions? All right. Let me begin by saying, I guess, two things. First of all, let's consider something very simple but rather important. Suppose we take a limit, a low temperature limit of this thing, H minus E0 over KT. Well, what is this? Well, this is the same limit my left arm is down, so you need to be careful. We put in the sum of energy eigenstates. And so this thing is then a limit again of big T goes to 0, e to the minus En minus E0 over KT times N. And as you take, when assuming that these energy levels have some spacing, then this is just the ground state. So the point is that this that e to the minus h over 0 is proportional to a projection operator on the ground state of the system. And this is the basic idea behind Euclidean quantum field theory and behind lattice gauge theory and so forth. So this is actually an important but very simple result. A couple of integral formulas. Integral minus infinity to plus infinity, e to the minus IA x minus, I'm not quite sure why I wrote this in such detail. dx. In any event, this is equal to square root of pi over IA. So this is a standard Gaussian, but it's in fact, notice there's an I here. So it's sort of an imaginary Gaussian
Can
integral.
I ask a question?
Yes,
Before that, why are we taking the low temperature limit at all? In the
because otherwise, if you do the high temperature
then why do
limit,
we need a limit at all? Why not just some finite temperature? Why does the limit?
oh, if you're at a, well, the real reason is that, if you're studying QCD, the strong interactions, then the temperature scale is, I don't know, 200 or 300 MeV. And so room temperature, much lower by a great deal, because 1 EV is something like 10,000 degrees in somebody's temperature scale. So that's basically the reason. The other thing is that in, quantum field theory, as you no doubt appreciate, is extremely complicated. If we're going to understand anything, we're going to understand the ground state and maybe a state of one particle or two particles or a few particles. So that basically is the idea. It's the opposite point of view from condensed matter physics, where you have lots and lots of particles. And here, let me give you a candy. Oh, good. So we've got one completion at least. This, by the way, works for AB real, and notice why AB has to be, well actually A could be more general perhaps, but the main thing is that, well, it may be a little more general than that, but in any event, it works for A and B real. Another one that's important and that we'll use is e to the minus r. This is your standard Gaussian. And I'm not quite sure why, again, I had c over 2r, because the c doesn't make any difference. And this is pi over r. So in both cases, we get something simpler, but we can then derive from these a slightly more complicated relation. E to the minus I a x squared plus I bx dx. Well, this is square root of pi over IA e to the I b squared over 4a. And this one implies that the integral e to the minus r x squared plus cx dx is square root of pi over r e to the c squared over 4r. That's an r. Okay, so these are, the bottom row are simple Gaussian integrals. This one is proven in chapter 5 of my book by means of a contour integration. In any event, these two things we can then turn into formulas that we're going to be using, namely minus infinity to plus infinity, e to the minus epsilon p squared over 2m, plus I epsilon q dot p dp is square root of 2 pi m over epsilon e to the minus epsilon 1/2 m q dot squared. And so you see what's happening here is you're going from basically a Hamiltonian and a phase factor into something that looks more like a Lagrangian. The top one is similar. It is integral minus infinity to plus infinity e to the minus I epsilon p squared over 2m plus I epsilon q dot p dp, and this is square root of 2 pi m over I epsilon e to the I epsilon half m q dot squared. So in both cases, you see, you're going from Hamiltonian, the kinetic part of the Hamiltonian, either with a minus epsilon or a minus I epsilon to something that looks like this q dot squared over 2n, which is our standard kinetic energy formula. I'm going to skip all those I'm following chapter 16 of my book on path integrals. I put it on the web page. And I'll add in a few things from Schwartz's treatment. In fact, I encourage you to read Schwartz's treatment also. He puts in some things that are worth saying. Okay, so we see that this thing is a projection operator on the ground state, or at least proportional to 1, and obviously these integrals that are standard Gaussian integrals make more sense mathematically. So let's start there. The idea is one that might have been originated by Schwinger. I think Schwinger and Martin did some fundamental work on quantum statistical mechanics back in probably in the 50s and 60s. Martin, by the way, his initials were PC, and I never had a class from him, but I talked with postgraduate students who had classes with him, and they said that Martin would lecture, and his TA would be there in the audience somewhere, and the two of them were basically talking the whole time, and the students really didn't understand what was going on. And in fact, they called him partly cloudy Martin, because that was, the reference there is that the New York Times, which of course was available in Cambridge the same day, and the headline, if you looked at the New York Times, on the right-hand upper corner was a weather report for New York, and it was always partly cloudy, almost always. And so that's why I hope he doesn't watch this. But anyway, he eventually became a dean. Okay, e to the minus IHT. This is the time translation operator. If you then send t to minus I beta h bar, then this thing goes to e to the minus beta h, and here we're thinking of e to the minus h over kt, because beta is sort of a standard formula for inverse, a standard symbol for 1 over Boltzmann's constant times the temperature. Any questions? So now let's do a path integral for, let us say, a sort of standard Hamiltonian, and I'll just think about quantum mechanics of a single variable q, and so we have here qp commutator is IH bar in unnatural units, or I in natural units. Oh God, I've violated the de Blasio rule again. Sorry. Anyway, let me just say it because I hate to write with chalk. So I'm going to be explaining how to do path integrals and deriving them for these two cases of statistical mechanics and quantum mechanics, and for just one variable, then go to a couple of 2 or 3 variables, and then show you some of Feynman's tricks. It was Feynman who was the person behind these things. Although there was a, you know, Dirac essentially thought of everything before everybody, and he had some ideas about path integrals. I don't know the history in detail, but I would guess so that, I mean, it's basically Feynman. Okay, so here is the key approximation. E to the minus epsilon, so we're in the stat mech case. P squared over 2m plus v of q. Now, we're going to say that this is approximately e to the minus epsilon p squared over 2m, e to the minus epsilon v of q, and then, of course, it's plus terms of order epsilon squared. And so we're going to be looking at this in the limit of epsilon going to 0. That's the idea of path integrals. There's a mathematician named Trotter worked on these things, and he basically proved that under various conditions, what we're doing here is legitimate, and it's called the Trotter product formula. Okay, we're going to be using the identity operator in various forms. One form is an integral minus infinity plus infinity p prime, p prime, p prime, and I'm using a prime to distinguish between the eigenvalue and the operator. The unprimed thing is the operator. The unprimed q is the operator. Q with a prime is an eigenvalue. Okay, well, we know the inner product, q double prime, p prime, it's e to the I, q double prime, p prime, over square root of 2 pi. This square root of 2 pi, by the way, it's, of course, in unnatural units, it's 2 pi h bar. H bar is h over 2 pi, so 2 pi h bar is really h. So in real units, this is the square root of Planck's constant. In general units. I shouldn't call them unnatural, but I can't resist. All right. Okay, so now let's compute this thing. Q double prime, e to the minus epsilon h q prime. Let's see what this is. Well, minus infinity plus infinity. I'm going to insert, I'm going to first of all use this approximation. So we're going to have e to the minus epsilon p squared over 2m. But now we're going to insert a complete state, a complete set of p states, and then we're going to have the rest of this approximation. Okay, so this is, at least to order epsilon, a correct formula. And now you see this is an eigenvalue, eigenvector of that operator. This is an eigenvector of that operator. And so what we have is e to the minus epsilon v of q prime, integral minus infinity plus infinity, e to the minus epsilon p prime squared over 2m. And maybe I'll do this in a couple of steps. Q double prime, p prime, p prime, q prime, p prime. But we know what these are. These are these standard phase factors, which of course are all important. I mean, most of quantum mechanics is in here. especially when you realize you're supposed to divide by h bar, which makes the argument of the exponential dimensionless and sets the scale of quantum mechanics. So if we use this formula a couple of times, what we get is e to the minus epsilon v of q prime, integral minus infinity to plus infinity, e to the minus epsilon p prime squared over 2m, plus I q double prime minus q prime p prime dp prime. Okay. Oh, divided by 2 pi. We have two of those square roots. Or equivalently, Planck's constant. Okay. All right. Now, we can now use one of these integral formulas, and in fact, the right one to use is this one. Replace p by p prime r. And now, what about this thing here? Q double prime minus q prime. There's no epsilon here. So we're going to use a very suggestive notation. We're going to say that q prime dot, sort of time derivative. We're going to say that that is q double prime minus q prime over epsilon. So it's kind of a notation. And at that point, this thing is e to the minus epsilon v of q prime integral minus infinity to plus infinity e to the minus epsilon p prime squared over 2m plus I epsilon q dot p prime and q dot prime. Prime refers to this q prime. dp prime over 2 pi. And now we have something that's exactly in this form. And if we do the integral, what we get is m over 2 pi epsilon to the 1/2 e to the minus epsilon 1/2 m q dot squared prime plus v of q prime. Okay. So in other words, this matrix element e to the minus epsilon h between two q states is a factor which eventually will cancel actually. And then e to the minus epsilon and the kinetic energy written in terms of q. So it's a 1/2 mv squared plus v. All right, so that's the basic idea of path integrals. Everything else is basically downhill from here. And in fact, when I say downhill, we haven't gone up a very big hill. So path integrals really aren't difficult, but there is a certain magic here, and let me just confess that or point out a problem here. You see, I assumed that the Hamiltonian was quadratic in the momentum. If it's not quadratic in the momentum, we have a bit of a problem. And in fact, typically, if it's not quadratic in the momentum, and we're starting from a Lagrangian, typically we either can't find the Hamiltonian, or if we find it, it's so complicated we don't know what to do with it. Okay. So there are certain limitations to, in other words, what I'm talking about here is almost the most general thing, for at least bosons. All right, well, the next step is to link two of these things together. So we have Q triple prime e to the minus 2 epsilon h Q prime. And of course, this would be integral minus infinity to plus infinity Q triple prime e to the minus epsilon h Q double prime e to the minus epsilon h Q prime dq double prime. And there I'm just using the standard identity operator in the form dq prime, q prime, q prime, minus infinity to plus infinity. All right. Okay, well, we know what these two things are, so putting them together, we will just have m over 2 pi epsilon, because the two square roots give us that. Then we have an integral minus infinity to plus infinity, e to the minus epsilon, and we have a half m q dot double prime squared plus b of q double prime plus a half m q prime dot squared plus b of q prime. So that's dq double prime. So that's what we have. Now, if we put 3 of them together, so we have, say, q3, e to the minus 3 epsilon h, q0, then what would we have? I'll just give you the answer. The answer is m over, of course, 2 pi epsilon to the 3 halves integrals from minus infinity to plus infinity, e to the minus epsilon, and now we have a sum, j equals 0 to 2, of a half m q j dot squared plus b of qj. And what are we integrating over now? dq1, dq2. So we have a double integral. So you can imagine what the next step, I'm not going to do 4, no. We're going to jump to n. And so q sub n e to the minus n epsilon h q0 would then be lots of integrals, qn e to the minus epsilon h, qn minus 1, qn minus 1, dot, 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 q1 e to the minus epsilon h, q0, and then we would be dq1 dq n minus 1. There's always one fewer integration. The number of integrations is one less than that number if this one's 0, and if that's n, there are n minus 1 integrations. Okay. What we do now is I'm going to set dt equal to epsilon, or epsilon equal to dt. In a sense, it's not dt, it's really d beta, because we're in this stat mega point world. But so you can think of it as that or d beta. So you think of it either way. And then we're going to be taking the limit as this goes to 0, and as n, which is beta over epsilon, goes to infinity. And in fact, there's sort of a double infinity here if we want to get something proportional to the projection operator on the ground state, then we need to take the limit beta goes to infinity, which is what I started the class lecture with. So we're taking beta to infinity and epsilon going to 0. So this n gets to be a huge number. Okay. And so that's a sort of frightening aspect of this business. But anyway. Okay. So let me get to the next step. What we get here when we do those, we string all this together, we know that we'll just have m over 2 pi epsilon to the n over 2, and then we'll be integrating minus epsilon sum now, j equals 0 to n minus 1, a half m qj dot squared plus v of qj. So all times epsilon, and we can think of that as d beta or dt, and then of course we have dq1, dq n minus 1. So that's the picture, and now if we imagine that we go to this limit where beta goes to infinity, epsilon goes to 0, and n goes to some dizzying number much larger than 2. Then what we have is basically q sub beta, effectively, e to the minus beta h q0 is then effectively nm over 2 pi beta to the n over 2 integral e to the minus integral 0 to beta half m q dot of t, let us say, plus v of q of t dt, and then dq1 dot 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 dq n minus 1, where this n, of course, is a stupendous number. And what we normally do is we just say, well, we can't keep track of this. And we're, in reality, the only thing you ever can trust in the world of path integrals, or the only thing you have a prayer of computing, is the ratio of path integrals. Okay? So you don't need to worry too much about this crazy factor out in front. So what we do, the traditional thing, is to just say e to the minus integral 0 to beta of, again, half m dot squared t plus v of q of t. We write it as capital D of q, meaning that we're integrating over basically all paths q of t that go from q0 to q beta in an imaginary time t beta, or just I mean, in reality, what we're talking about here is we're integrating over all functions q of t, such that q of 0 is q0, q of beta is q sub beta, and we integrate this thing, and dq means we sum up the whole business. And once again, we're only going to be using ratios of things like this, and so it's going to be all right. So I started out talking about 1 dimension. If we go to 3 dimensions, there's no change conceptually. We just have this q vector beta e to the minus beta h, q vector 0, integral e to the minus integral 0 to beta. And if I put in h bar, then this is m over 2 h bar squared q dot squared of beta prime v plus v of q of beta prime d beta prime. So if I really write things down in a totally putting in all the units, then you see what we've got is a little more peculiar than it's a little bit stranger than what we had to start with. This isn't just m over 2 q dot squared, it's an h bar squared there. And then, of course, this thing is, if I put in all the units, it's nm, well, n over 2 pi beta h bar squared 3n over 2, and then this of course is dq1 up to dq n minus 1, where of course this is a horrendous number. Okay, this is called Euclidean space because when you go to field theory, the Lagrangian, or the kinetic term of the action, has all the derivatives with the same sign, and so you don't have to worry, is it Weinberg's metric or Schwarz's metric? All right, now let's do the case of ordinary time and quantum mechanics as opposed to stat mech. So it's a, yes.
Are there any restrictions on these paths that we're integrating?
Good question. Are there any? They're going forward in beta.
That's it.
Yeah.
Well, it's just a little bit confusing because some of these paths might not even necessarily obey any kinds of equations of motion, like classical particles.
Oh yeah,
So
absolutely,
they could be
absolutely,
discontinuous,
yes.
And so,
Yes. Do you want a candy?
no, thank you.
Good question. Not only that, but you know, if we were on the other side of Lomas, then and we're mathematicians instead of physicists, then we'd worry about, well, these things could be discontinuous paths. Okay. Turns out, all right, here,
Maybe they
I
have
mean,
a set of measures.
I should, well, it may be that the continuous ones are a set of measures 0 instead of all paths. First, however, notice what happens. If this thing is discontinuous, then this thing is infinite. We've got a minus sign, so those are terribly discouraged. All right. So the thing makes sense, and I'm not a mathematician, so you don't want to really believe anything I say about mathematics. Anyway, let's do, let's repeat what we did before for the time evolution operator. So once again we go to the simplest case. We use the approximation that we're going to write this as a p term times a q term as long as epsilon is tiny. So this gives us integral minus infinity plus infinity q double prime e to the minus I epsilon p squared over 2m. We're going to say that we put in the p prime states, complete set of states, e to the minus I epsilon v of q prime p prime. Once again, this is an eigenvector of that operator, this is an eigenvector of that operator. We know what the inner products are of q double prime with p prime. It's a phase factor to the I q double prime p prime divided by square root of Planck's constant. And so what we get is 1 over 2 pi e to the minus I epsilon v of q prime, which of course comes from there, and then an integral e to the minus I epsilon p prime squared over 2m plus pi p prime q double prime minus q prime And now we do this sleight of hand where we say, we're going to write this as e to the minus I epsilon b of q prime divided by 2 pi. And integral e to the minus I epsilon q prime squared over 2m plus I epsilon q prime dot p prime dq prime. And we do that integration, we use one of those integral formulas, the one for the one that's based sort of a Fourier, I don't know, it's a Fourier transform. Anyway, yeah, well, anyway, we use the other integral formula, and what we get is that this is actually m over 2 pi I epsilon to the 1/2 e to the I epsilon m q dot prime squared over 2 plus v of q prime. Okay. And now, this is the essence of it. As I said, the rest of it is downhill. This is, if you think of epsilon as dt, then this is a little bit of action. The action being m q dot squared over 2. And actually this, I screwed up, there's a minus sign here. Because the Lagrangian has, well, e to the minus I, that was the minus sign, okay? And the Lagrangian, of course, is kinetic energy minus potential energy. Okay, so that's the case for 2. Now, instead of doing 3 and so forth, let me just go to n. So we have q sub n, so this is real time, this is ordinary quantum mechanics. E to the minus I n epsilon h q0. It is then m over 2 pi I epsilon to the n over 2 integral e to the I epsilon sum j equals 0 to n minus 1 1/2 qj dot squared minus v of qj, epsilon functioning as essentially dt, and we have dq1, dq, n minus 1. Okay, so that's basically the path integral formula, and we now take the limit n going to infinity and epsilon going to 0, so that the time interval n epsilon is finite, some finite interval. And we then rewrite that as q sub t e to the minus I th q sub 0 is an integral e to the I integral 1/2 m q dot squared plus v of q over t dt, well, dt prime, so 0 to t, and then we just say big T of q, where we're interpreting it the way we did in the upper one. Yes?
What is this matrix element?
What is it?
Yeah.
Well, it's the amplitude to find a particle that was at q0 at time 0, the amplitude to find it at time t at q sub t. That amplitude is what we're just computing.
Okay, so we have two different kinds of Q then. Like
2 different kinds of what?
Q, like we have points, right, for the matrix element, but then dq is actually an integral over all paths.
Right. We're integrating over all of those intermediate states,
Oh, okay.
and And another way of writing it, since this is another way of writing it is integral e to the I integral L dt prime 0 to t dq. And now another way of writing it is e to the I s dq. But the s is an s that is for paths that go from q0 to qt in time t. And the only thing about these paths is, if you think about it, summing over paths is we go forward in time, we don't go backward. We always are going forward in time. All right, any questions? Three dimensions, of course, the analogous formula, well, all you do is write vector sums.
I have a question.
Yes,
What is that capital DQ?
capital
Because it seems we have
D of capital
right.
DQ? Ah,
we have
good
infinite.
question. Well, DQ is this factor times all of these integrations.
We have infinite term.
Huh?
We have infinite n. We have infinite n.
Yeah, we have to take n going to infinity.
So how can you write it down?
What do you mean, how do you can write it? All right, hold on. How many people didn't get candy and asked a question? Pause for TA. Anybody else? All right. So let's see. All right, I mean, to be quite honest, this is a this is, how shall I say, it's a pretty, from a mathematical point of view, it's well, basically it's new mathematics. I mean, what we, 300 years ago, Newton and Leibniz introduced calculus, and it was a new idea. Like, probably the idea of limits was new. Well, Feynman introduced this, and what would be really nice would for somebody to do to path integrals what Newton and Leibniz did to calculus. And well, so far there's been some progress, and it's sort of outlined in these notes. There isn't much more beyond what's in the notes. And actually computing things, well, the way one does it is one can compute ratios of path integrals by using Monte Carlo techniques. And these work quite well for the StatMech case. They don't work so well for the real-time case, in other words, the quantum mechanics case. But on the other hand, if you're studying the vacuum and you really want to understand that, then it's the Euclidean case that you want anyway. So that's not such a bad thing. That's not such a big drawback. All right, so I think we've got. All right, now. All right, let me point out one thing that would cause, that certainly causes me pause. Epsilon is real. There's an I here. We're sending n to infinity. 1 over epsilon. Epsilon's going to 0. This is sort of infinity. There's an I. So this infinity is and a square root. So this is sort of like 1 over square root of I, okay, raised to a power n over 2. So square I is, you know, up there, 0, 1 in the complex plane, right? Square root of I is sort of at 45 degrees, and then this thing is telling you, well, just spin it around an infinite number of times. So this is pretty crazy. On the other hand, as I said, it's really ratios that matter. This is particularly obvious in the stat mech case. But if we can arrange it in the quantum case, then these crazy factors out in front cancel. All right. Now let me show you that although the mathematics here can be striking and make you feel as though nobody could ever understand anything about this. In fact, there are some things that are really quite simple. And I'm going to tear up the script for a minute and try to give you the basic idea. So what we've got here is this amplitude is this thing here. Okay. Suppose now I want to consider two cases. The first case is that somehow I feel better if time is going to the right. I don't know about you. And if time is going to the right, then let's say Q0 is here. So this is Q, and this is this QT that we're talking about. So we're talking about paths that from time 0 to time t go from this position to that position. So it might be a straight line, it might be something like that, it might be something like this, and you have to sum over all of them. Okay. Now, notice that what we can do is we can write this S of Q, which is an integral of m over 2 Q dot squared plus d of Q dt. We can write this as, well, let's suppose that the time interval t that we're talking about and the points Q0 and Qt are such that there's a classical path joining them. All right. So what is a classical path, of course, is a path for which the it's a path for which the action is stationary. That is to say, if you vary the path a little bit, the change in the action is second order in the change in the path, rather than first order. And so in that case, you see, we could write this thing as an integral m over 2 q classical plus delta q dot squared plus v of q classical plus delta q dt. So this would be the general action that would go in here, and then we sum over all of them. All right? Now, something magical happens that Feynman noticed, I think, when he was a graduate student. If there is such a classical path, then the first order term, when you expand these two things, the first order term is 0. So what we get here is m over 2 q classical dot squared plus v of q classical dt. The next term is 0, but I'll write it out anyway. M q classical dot delta q classical dot plus v prime at q classical delta q Well, it's not delta Q times, it's delta Q. Okay. dt. I forgot the dt, because all this is dt. And then the next term is it's, well, whatever's left. And in this particular case, it's m over 2 delta q dot squared. So that's pretty simple. And then it's a half v double prime of q classical delta q squared dt plus higher order terms of delta q. Okay. Notice there aren't any higher order terms for the kinetic part. Okay. This term is 0. Why is it 0? It's 0 because if you integrate by parts, what you get is minus m q double prime classical plus v prime of q classical delta q dt integrated, but this is just 0. This is the classical equation of motion. No, it's a minus sign here. That's why it didn't look quite right. It's kinetic minus potential. Left arm down. So this is minus. And so then if you write this as an equation, it's mq double dot equals minus v prime q. So this term is 0. And then there's something else. In the case of which v, if v is quadratic, then this is the end of the story, because there aren't any higher derivatives. If it's not, then we have a long story here. We have to sum the whole business. Okay. All right, so what do we get? What we get is that the action is S classical plus the rest of the story, which is well, I shouldn't have put two things together. I was trying to do too much. Anyway, it's S classical plus something that's proportional to delta Q squared. So it's some integral dt of delta Q squared times something or other. I'll write something other as a Chinese character. Okay. Now, let's look at how this action, now let's look at the amplitude to go from here to there. Well, it's going to be a sum of these things. And so what is it going to be? It's going to be the amplitude then, I'll just say equals, well, it's going to be e to the I S classical, and then it's going to be this stuff here that is sort of an e to the I delta Q squared dt integrated dq and so forth. And the idea basically is that as we add up all these paths, because this is the square of the change, the phase change is smaller than if it were, if we didn't have a classical path. So in other words, if we had a final, a Q, a different Q, say up here, and there wasn't any classical path, it would go from there to there in time t, then all of the paths would be such that this term would be linear in delta Q. And then what we would have would be that the amplitude was an integral of e to the I integral delta Q dt. So it would be all sorts of things like this, and the phases would cancel. So in other words, what we're deriving from this is that the the amplitude, if there's a classical path, then the amplitude to get there is big compared to the amplitude to get somewhere when there isn't any classical path. So in other words, classical physics is a consequence of the path integral. Now, suppose the action is suppose the potential here is only quadratic in V. Then we've got something that is quite remarkable, namely, this thing terminates, and this is it. In other words, we can say then that S of Q is S classical plus 0, because I'm talking about the case where there is a classical trajectory. And then plus this thing here, which is S of delta Q. Okay. And this S of delta Q, you see, is this time integral of this thing. And what is delta Q? Well, delta Q, you see, is the path from 0 to 0. In other words, it's a loop that goes from here, does whatever, and then comes back. Let's see, I drew that so that it's going backward in time, so that's stupid. What I mean is, there's 0, it goes up or down or whatever, and then comes back. So it's a loop in this sense. As you go from 0 to t, you're going from 0 to 0. All right. So, what does that mean? That means that, moreover, actually, let me say something else. If this thing is just quadratic, then we can write V of Q is V of Q classical plus delta Q. And so this is a V of Q classical. That goes into the classical action. The linear term cancels, and the other term is just, in other words, we're expanding this in powers of this. The other term is V of delta Q. And it then is independent of the path. In other words, it's, maybe I should just write it down. You have V is going to be A times Q classical, well, it's going to be A. Then it's going to be B times Q classical plus delta Q classical. And then it's going to be C times Q classical plus delta Q squared. All right, so that's the classical, that's the potential in the quadratic case. If you expand this out, what you get is that the terms involving QC go into SC. The terms that are linear in delta Q cancel because there is a classical path. And what's left is A plus C delta Q squared. Okay. So that means that this thing is S of delta Q, and there's no Q classical anymore here. So that's quite remarkable. That means then that you can compute the path integral to within a factor of a function of time. That is to say, you can say that the amplitude to go to qt e to the minus I th q0 is the classical action e to the isc times this loop integral delta q. But everything over here has no reference to Q0 or QT. It only had the only thing it knows about is the time interval. And it's the integral of the action of the loop. Loop in the sense of that it goes from zero space to zero space in the time t. And so this is just a function of t. So the answer is some function of t e to the I as classical. Okay, so that's a case in which the whole path integral business becomes very simple. Now I'm thinking about this, it just occurs to me that, as I said to you earlier, you really can't get off the ground unless the Hamiltonian that you start with, or Lagrangian that you start with, is quadratic in the momenta. In other words, the Lagrangian better be q dot squared plus some function of q, and h had better be p squared plus some function of q. Otherwise, you've got a problem. A linear term in q dot is probably okay, but something more complicated isn't. Now what we see is that if the potential is also quadratic in q, then we almost have nothing to do. We can write the true quantum mechanical amplitude as a function of time times the phase of the classical action. And you can also often puzzle out what f of t has to be, because you know that the amplitude to go anywhere in time 0 is essentially 0 unless you go nowhere. And so the limit of this thing as you send t to 0 has to be delta of q sub t minus q sub 0. And so that often tells you what f of t actually is. Or at least it gives you some idea of what it must be. All right, so that's that. I don't know whether it was a good idea for me to depart from the notes so much, but all right. Well, one further thing is showing that Schrodinger's equation follows from this. We've got 4 minutes. Maybe I can do it. All right, so let's see how this goes. All right, so the first thing is we have q double prime e to the minus I epsilon h. So we're talking quantum mechanics, not stat metrics. And we've seen that this is m over 2 pi I epsilon to the 1/2 e to the I m q double prime minus q prime squared over 2 epsilon minus I epsilon v of q prime. So that's another way of writing what we had. We were previously writing that as I epsilon m over 2 q dot squared, but q dot was defined this way. Okay. So let's use this to write psi. Now we're talking time t plus epsilon. And this is then integral q double prime e to the minus I epsilon h q prime psi of t dq prime. Okay, so in other words, we've just put an e to the minus I epsilon h in there, and so that gives us this. And then this thing is that, and so this is m over 2 pi I epsilon to the 1/2 integral e to the I m over 2 epsilon q double prime minus q prime squared minus I epsilon b of q prime psi of t q. Okay. Now we're going to expand this and keep terms of just of order epsilon, and so what we get is this thing, m over 2 pi I epsilon to the 1/2, e to the minus I epsilon v of q double prime. I see here double prime, and all right. Integral e to the I m double prime minus q prime squared over 2 epsilon psi of q prime and t dq prime. So I haven't really done very much there. But now the trick is to let q prime minus q double prime equal x, so that q prime is q double prime plus x, and then we can rewrite this equation as psi of q double prime t plus epsilon is this square root of m over 2 pi I epsilon e to the minus I v of q double prime integral e to the I m x squared over 2 epsilon psi of q double prime plus x t dx. Okay. So now we're going to expand this and in x, and so it's going to be a linear term plus a quadratic term in x, and then we're going to expand this in epsilon, and so what do we get? We get psi of q double prime plus x t is psi of q double prime and t plus x psi prime of q double prime and t plus a half x squared psi double prime of q double prime and t, and of course psi of q double prime t plus epsilon is psi of q double prime and t plus epsilon psi dot of q double prime t. Okay. So now if we take these two expansions, stick them in here, and keep terms linear in epsilon, and we use these integral formulas which I've carefully erased, and we use one more, namely the extra integral formula is integral x squared e to the I m x squared over 2 epsilon dx. Well, this is I epsilon over m 2 pi I epsilon over m to the 1/2. And the integral of a single x with this dx is 0. And the reason why we want to do those integrations is we have e to the I m x squared over 2 epsilon times this. When we expand that, we get the linear term, we get the x squared term. Okay. If you do all the high school algebra, then what you find, I'm going to use this board over here because there's a little bit of space left. You get psi of q double prime t plus epsilon psi dot of q double prime t is expanding that exponential 1 minus I epsilon v of q double prime times psi of q double prime and t plus I epsilon over m psi double prime of q double prime and t. Now, if you cancel the one term, this term with that times that, and then keep the terms that are linear in epsilon, then what you get, I'm going to use this little space down here, you get I psi dot is minus 1 over 2m psi double prime plus v psi. So that's Schrodinger's equation. So, in other words, you derive Schrodinger's equation from the path metric. And so that's nice. Sorry about going over slightly. Any questions?